When you observe something in the world, from a tree to a school bus to a bird, you know that regardless of where and when you observe the object, it will remain the same. However, what if I told you that the time and manner in which you looked at a bird would affect its appearance? That might sound absurd, but absurdity is to be expected when it comes to the quantum realm. The field of quantum mechanics is primarily founded on three pillars, beginning with quantized properties. Quantized properties give the position, speed, color, and other properties of a particle that can only occur in set amounts of time and instants. This is in direct contrast to the field of classical mechanics, wherein everything happens in a smooth and continuous spectrum. The second pillar of quantum mechanics refers to the particle nature of light. At first, the notion that light could behave and be classed as a particle was disbelieved, as it ran against the well-established principle of light's wave-like nature. However, the particle nature of light introduced a fundamental unit representing tiny energy packets, known as quanta. The third and final fundamental pillar of quantum mechanics is the wave nature of matter. The wave-like nature of matter was independently proposed by two scientists around the same time, despite being oblivious of each other's work. Louis de Broglie and Erwin Schrodinger used two fundamentally different mathematical approaches to prove this wave-like characteristic of matter. When a quantum observer is watching, quantum mechanics states that particles can behave as waves. When behaving as waves, electrons can simultaneously pass through several openings in a barrier and then meet again on the other side, a phenomenon known as interference. However, this can only occur when no one is observing it. Once an observer begins to watch the particles going through the opening, the obtained image changes dramatically. If a particle can be seen going through one opening, it is clear that it did not go through the other opening. In other words, when under observation, electrons are forced to behave like particles instead of waves. Thus, the mere act of observation affects the experimental findings. To demonstrate this phenomena, researchers built a tiny device, less than 1 micron in size, possessing a barrier with two openings. They then sent a current of electrons towards the barrier. The observer in this experiment was a tiny electron detector that could spot the presence of passing electrons. The very presence of the detector observer near one of the openings caused changes in the interference pattern of the electron waves passing through the openings of the barrier. When the observer's capacity to detect electrons increased, or when the level of the observation went up, the interference weakened. When its capacity to detect electrons was reduced, the interference increased. Thus, by controlling the properties of the quantum observer, scientists managed to control its influence on the electron's behavior. The observer effect may be hard to wrap your head around, but it's a key aspect of understanding the mysterious world of quantum mechanics. If you enjoyed this video, we'd love to hear from you in the comments section. Your feedback not only supports us, but also helps our channel reach more viewers and continue to grow.